In this part of the lesson, we're going to look at rational exponents before we go into the radical equations, because we will use those to solve equations. A rational exponent is defined as a value raised to a fractional exponent. Rational just means a fraction. So what this does is it turns something into a radical. All right, when we think about a rational exponent, we often use the 1/2 exponent. That's because 1/2 is the exact same thing as saying the square root of x. So if you had a x to the 1/3, this would be the same as the cube root of x. And if we keep looking at the patterns that we see, x to the 1/4, 1/5, 1/6, whatever that bottom value is, so let me do 1/n, will tell us the radical or the root that we're taking. So this would be the nth root of x. Now all of these are x on the inside, and it's to the first power because the numerator of the fraction was 1. But if we had a value up top in that numerator that wasn't 1, that would become the exponent inside of the radical. So the format of it will follow the nth root of a to the m power. So I just write that as a to the m over n means power over root. So the m is our power, n is our root. So we get the nth root of a to the m. So if we kind of convert these a little bit, if I have the cubed root of x squared, the cube root, that becomes our denominator because that's the root we're working with. So I'm going to say x to the 2/3 because I have an x squared. So 2 becomes the power, root is 3, so 2/3. For number 2, r is going to be to the first power inside of that radical, so it becomes r to the 1/4, since we have a 4th root. 3 is a little bit different. We have a fraction where the square root is in the denominator. If you remember things about putting things in the denominator, let me go ahead and switch this first. So this will be 5 to the 1/2 power because it's the square root. But if I have a negative exponent, what that did was move it down to the denominator or move it back up to the numerator. So it switches the sides of the fraction. So I'm going to make this 5 to the negative 1/2, and now that's just gotten rid of the fraction part. For 4, the 5 is outside of that radical. But that's the same thing as if it had been inside, b to the 5th. That's happening because what we're saying is we have 5 of these things. So if let me just put this on a sticky note. If I wrote that out 5 times, it would be kind of annoying, but I can. And when we multiply radicals, we're multiplying the inside. So that would still say the cube root of b times b times b times b times b. So that's why we can rewrite it as to the 5th power there. Now that it is following that same format as all the others, we can write that as 5/3 power over root. If I work backwards and go the other way, we want to write these from a rational exponent into the radical. So let's convert. I have 4 to the 1/3. It's power over root, so that means I'm taking the cubed root of 4 to the 1st, which is just 4. Number 2, power over root, so it's still a cube root. It just is the cubed root of x squared. 3, you see that negative exponent. So let's get rid of that negative exponent first. What it does is it moves it down to the bottom. So now it's y to the 3/2 in the denominator. But then we can convert to a radical. So I would have a square root since the denominator of that fraction is 2. So I'm going to write a square root of y cubed. If you remember back, we just talked about 1/2 is the square root. We don't write a little 2 there often because it's implied. A square root symbol is an automatic root 2. So you don't need to write a little 2 in the index there. Number 4, I think, is the trickiest one, and students mess this up the most because what we have is an a to the negative 3/2, but the 5 isn't associated with it, with the exponent. 5 is just multiplied. So if I had parentheses 5a to the negative 3/2, that would be different. But in this one, the 5 is not tied to the exponent. So I would rewrite that as 5 times. And then let's just see, how do I rewrite this? Well, it's to a negative, so that means I'm going to put it in the denominator. So a to the 3/2 now. And then, so I can just make that 5 over. But this is going to become a radical, which is the square root of a cubed. So just be careful, make sure that you're only putting under the radical what is associated with the exponent. All right, now we get to our graphing things, and let me zoom in a little bit more for this, because when we talk about graphing a radical function, it's helpful if we remember what the parent function looks like. So I'm just going to briefly, let me do this in red, graph our parent function. The square root of x. If we plug in values, the square root of 0, so if I said x was 0, the square root of 0 is 0, so I'm going to get 0, 0. Now if x was 1, the square root of 1 is 1, so the output's 1, so I'm going to have a point at 1, 1. If x is 2, I don't get a nice value. We can plug that in our calculator and see what is the square root of 2. But that doesn't come out nicely. It's 1 point something. So we want to think about what's going to give me a nice square root. Square root of 2 is not nice. Square root of 3 is also not nice. But square root of 4 is nice. So the square root of 4 is 2. So I'm going to go out 4 and up 2. And then we look for what's the next nice square root. So square root of 4, square root of 5 is not. Square root of 6, 7, 8, 9. Square root of 9 is the next nice one. Square root of 9 is 3. So I'm going to go out 9 and up 3. And we can see our radical function forming. If you think about what's going to be the next nice square root, it's going to be the square root of 16, then the square root of 25. So it'd be the square root of all those perfect squares. But it follows that same pattern for the shape of the graph, where we would go out 1, up 1, out 4, up 2, out 9, up 3. And we can use that just like we did with quadratics to apply transformations. So when I look at number 1, let's first describe some of these transformations. This minus 3 made the inputs move right 3. So I know it goes right 3. The plus 4 made it go up 4. We also saw the 2, which was a vertical stretch. That's outside of the radical. So it's a vertical stretch by a factor of 2. Okay, so if we apply those transformations to this function, that vertex part that was at 0, 0 will now move right 3 and up 4. So I'm going to take that and go right 3, up 4, and put my coordinate. All right, let me try to zoom in as best I can. The next part we want to do is put some other points. Now I found other points by going out 1, up 1. So if I follow that out 1, up 1 from the vertex, it would maintain that shape. But I don't want to make just up 1. I want this to be a vertical stretch by a factor of 2. So that vertical stretch, instead of going out 1, up 1, we're going to multiply that up by 2. So out 1, up 2. Gives me a point right there at 4, 6. All right, now we can go to the next coordinate on the parent function, and that was out 4, up 2. So I'm going to go from the vertex, go out 4, up 2, but now my up is being multiplied by a factor of 2. So instead of going up 2, I'm going to go up 4. So out 4, 1, 2, 3, 4, up 4, 1, 2, 3, 4. And then the last point I might try, let's see if we can do it, we'll go out 9 and up 3, but instead of up 3, we're going to multiply the up by a factor of 2. So I'm going to go up 6. So out 9, up 6. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6. Since we've got room, let's actually keep going. So the next nice one would be out 16 and up 4, but the up 4, it has to be multiplied by a factor of 2. So I'm going to go up 8. So out 16 would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and up 8. 1, 2, 3, 4, 5, 6, 7, 8. We've got that part. We might even have room to keep going, so I could go out 25 and up would normally go 5 because the square root of 25 is 5, but we have to multiply that by a factor of 2, so up 10. So if I go out 25, let's see, I'm starting out at 3, so 25 plus 3 is 28. 28, okay. And then we would go up 10. So 4 plus 10 is 14. Puts me right there. But we have made a very detailed graph of our function. We just applied all those transformations. So when I do the second one, we're still following the transformations. This one went left 2 and up 3. But that negative is a reflection. So that reflects over the x-axis. So we're just going to flip that down. So instead of going out 1, up 1, out 4, up 2, out 9, up 3, we're going to be going down instead. So it'd be out 1, down 1, out 4, down 2, and so on. So let's find that vertex first. Left 2, up 3. Left 2, up 3. There's my vertex. And we're going to follow the out 1, down 1. So out 1, down 1 puts my point right here. There's no vertical stretch. I can go out 4, but that would go down 2. So 1, 2, 3, 4, down 2. Remember, I'm going from the vertex here. So I would go out 9 and down 3. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3. We could keep going out 16 and down 4. So let's see, this was out 9, 10, 11, 12, 13, 14, 15, 16. And we're going to go down 4. We keep going. So that was 16. Let's go out 25. We went backwards 2. So 25 minus 2 is going to be 23. So it gets me out to 23 and all the way down 5. That's enough points for this, but we can see the pattern that we're going. If we wanted to keep making points, we can. All right, so we have enough that we can now start trying to solve the radical equations in the next video.